Triumph. Oh, so I met him at the Triumph in mid 2000s, maybe like 2005 to 2007. I was a grad student back then, and he was a postdoc. And I remember him and Smartjit, which was Smartjit is one of the past students of Umesh. They were probably the loudest person in the working area at Triumph. So it's on the second floor, so it's basically cubicles, and you were hearing two person like speaking loudly all the time. They were Nico and Smartjit. Um, before going to Triumph, Nico did his PhD at the University of Brighton in the UK. I should say actually that he's originally from Spain, from Granada, where he did his undergraduate. After doing his PhD, he went to the University of Kentucky, where he spent some time as a postdoc. And then he moved from Lexington to Richmond in Kentucky, where he was there for as an assistant professor for a year. And then he went to Triumph. And then after that, after spending 2 or 3 years at Triumph as a postdoc, he became a lecturer and then went up the rank to full professor at the University of the Western Cape, where he is since. And Nico is normally a nuclear physicist, but with the COVID pandemic, he decided to play a little bit around with modeling, try to understand what's going on with all of those different waves that we went through. I think that's for the introduction. So I'll let you share your screen and welcome you to our virtual colloquium.
All right, Maxime, thank you so much. As I mentioned before, I really enjoy those days where we were discussing which masses to measure and which masses will tell us about the nuclear collectivity and so on and so forth. So let me actually go to my presentation, which is I'm not going to make a full screen because I want to move around, if you don't mind. Mm-hmm. So the title is "Can Epidemiological Models Predict Herd Immunity?" which is basically the same as understanding the validity of all these epidemiological models. And for why it's called herd immunity, I just was curious to understand why this concept. And it was here. Let me move this a little bit down. History was a term originated in the US. It was about abortion disease with cows. So people at that time, they used to sell the cows to different places and then make the problem even worse. So until some time, like in 1918, Adolf Eichhorn in Kansas, he wrote that we shouldn't be doing this, and he mentioned the concept of herd immunity as abortion disease may be likened to a fire, which if new fuel is not constantly added, soon dies down. Herd immunity is developed, therefore, by retaining the immune cows, raising the calves, and avoiding the introduction of foreign cattle. This is basically a very important concept in epidemiology, which is basically keeping the constant, the population constant. In this case, the population of involved, the susceptible, infected, and removal or death arising from the SIR model, which we're going to introduce in a little bit. Obviously, this herd immunity hasn't been very popular for various reasons. And nature has been always against the situation of believing in herd immunity, which is difficult to, as we shall see, we're going to see at the end what can we predict and what we cannot predict, the weaknesses of all these different models. And Nature is probably right to say that it's probably impossible, herd immunity. And here we have the promise of herd immunity, and how Nature blame a little bit the Trump administration for the whole mess in the US. But we won't go into politics here, although that play a big role for the situation in the US. But we're going to go step by step and think what we can learn from these models. So obviously, I just wanted to tell you that I'm a nuclear physicist, and as of yesterday, we have installed our new frame. This is called the Gamka frame, which means lion in the Bushman language of South Africa, the Khoisan language. And this is the new frame that we have installed yesterday, and everything fits beautifully. And as soon as we install it and took a picture, everyone related to the coronavirus here. So there's always a yin and a yang of a good and a bad thing for these kind of shapes, right? Hopefully, when we put the detectors in next week, it won't look more like a coronavirus thing. But for the time being, people thought at the beginning that we're making some kind of model of a coronavirus molecule. So today is my 20th anniversary, which I just learned like an hour ago, because I remember I have some pictures taken from my last visit in 2001, April 2001 actually. And this was, as I mentioned before, one of the first experiments with radioactive ion beams, which was done at the University of Notre Dame, but also I think worldwide. I think if Annie is there, she will remember this, but it was one of the first experiments with radioactive ion beams worldwide, which happened there at the University of Notre Dame. And we had a lot of fun with this experiment, which was quite difficult to achieve. But I remember Plamen here and we just were successfully claiming victory after we got some beams. After I think we solved some issues with the beam, with the electronics. This is the late Larry Lamb, a very nice gentleman who was always very welcoming. Here we have the big smile of Annie Abrahamian and myself. Here is the accelerator. This lady was called Emily. I have in the picture, but I don't remember what happened with who was her afterwards or anything about. So this is today. How do I know it's April 2001? It was because at the same time, President Bush Jr. came to Notre Dame to address the graduates. I mean, there was a graduation ceremony. And I remember suddenly there were many people, new people coming to the hotel. And there was this nice lady asking lots of questions. What are you doing here? Where are you going? So after a few days, this nice lady came with one of those military tanks once President Bush left the graduation ceremony. So she was probably investigating who were the visitors at Notre Dame campus, around Notre Dame campus. And once she was asking all these questions, we asked her, so we would like to eat one steak here at Notre Dame. We heard about this American steak. So where can we go and buy and eat one of those? So this lady, who belonged to the security, told us, okay, I think there's a place called Fridays or Yesterdays. I don't remember exactly what was the name. I said, okay, how far is from here? And she told us, it's like half an hour away from here. So obviously, us coming from Europe, we started walking. We walk and walk and walk for 30 minutes, for 1 hour, for 2 hours. After 2.5 hours, we had to call a cab, and it still was like 20 minutes drive to get to the place where we have the steak. So this was my first introduction to the American lifestyle, and I found this very, very, very funny. So now, let me continue, because this has been a collaboration, a massive collaboration, not only on the scientific case, which is interesting, but also on the awareness and the outreach, teaching and learning, you know, the things that came out of these investigations were new programs, new practicals, online pracs for students during COVID-19 times, you know, and they were used by different universities, University of Pretoria, UWC. We have run different mini schools. I will show you more a little bit about this, but it has been very welcoming on how everyone can model these things. These are some of the main characters of the story. Jose Enrique Amaro, he was my quantum mechanics professor at the University of Granada in Spain. And we introduced the Monte Carlo Planck. Today is the World Quantum Day. So we're going to relate the Planck's model of photons to our Monte Carlo simulation of COVID-19. Then we have also Jeremy Dudois, who is from the University of Lyon, and he's a big player at Ganil, doing all these data sorting, visualizations with the Agatha array. He's a computer genius, and we have developed all these different codes, which are very much automatized, and we can check what's happening at any country at any time, right? So I will show you more about that. And then this has been distributed to everywhere because we wanted people to know what was happening, you know, when we were deviating from the exponential phase. And this was, many people got involved. We got lots of friends on social media, but also not very good friends as well. They were criticizing the models at the beginning. What are you doing? You're not even an epidemiologist. You know, what are you doing? Doing all this nonsense? You know. So we came to some conclusions, which I will mention later. But actually, it was very nice to be able to differentiate. Our models will differentiate clearly between what was the exponential phase and the slowdown phase. You know, when you reach this plateau, what they call it the flattening of the curve. And then we apply mathematics. We did L'Hopital on the first derivative of these death functions, and we got the death rates, and we did lots of things applying mathematics. Our ideas of nuclear physics. You know, this is like a Wood-Saxon potential, but everything is like positive energies here, so there will be no binding. But you know, the shape is a typical shape of a Wood-Saxon potential. So then, finally, you know, for those critics, we got something published, and not only published, but this is one of the top journals in mathematics with an impact factor of almost 4. Global analysis of the COVID-19 pandemic using simple epidemiological models. Important to say here, let's actually zoom this one. Let's go a little bit on the slideshow from current slide so we can see it bigger. So the highlights of this paper were that we solved the SIR transmission dynamics equations analytically with, and this is the extended SIR model, which we developed as well, and without the T model for death model recovery assumptions. Our models can characterize the evolution of a pandemic at the different stages, exponential, normal phases, etc. Our models can be extended to describe additional space-time effects, such as the release of lockdown measures, different lockdown effects that happen. You know, you go from level 5 to level 3, 2, 1, all these things that we have throughout the world. Similar results from extended SIR and death models suggest that most susceptibles become infected, asymptomatic, and eventually recover. And similar trends suggest a common pandemic evolution with universal parameters, which allows, give us the hope that there may be a general solution to this problem, which hasn't been tackled so far successfully. I mean, this is not an easy problem. Otherwise, we'll know what will happen with the pandemic at all times, and we could make a better prediction and not believing, when science is not at the level, then we have situations where anyone can opinate, and things become messy. So this eventually became part of the Elsevier Public Health Emergency Collection, and now this paper is available for free. If you just click on this link here somewhere, I just I don't know if I put the link somewhere here, but basically, well, basically just can Google the title, put Elsevier Public Health Emergency Collection, and you will get it. Oh, I will send you the link. So anyway, that was the situation. And as I say, we have run many seminars, mini schools, and online pracs for those students who couldn't go to campus, to university. And we try to use a grim subject, as it is COVID-19, in a positive way. Always being positive, trying to do our best to keep the ball rolling, because the situation, as you know, was very complicated. So we had to take care of our students and our research, and we developed, as I say, new epidemiological models, and we did lots of data modeling and analysis. Everything was based on C++, Root, Python, Fortran, and we did these Monte Carlo simulations, basically things that we do in nuclear physics, like C++ based on Root, right? So all these kids who learn these methods, they're already prepared when they do nuclear physics. I'm talking about undergrad students. So when they go to do honors or masters or PhD, they're already familiar with all these tools. So I think this is a very interesting approach for us to speed up the process of transformation and of learning. So basically using same tools that we have in nuclear physics to COVID-19, to a topic which is very much interested at this time. And so here in this GitHub, you can find all the programs that we have developed throughout the last year and something. And it's nice, you can go to the YouTube videos also. If we just go here, here we go, I click twice, but if you go here, you have all the new codes, the old codes, some pictures of the plots that we made. You have here the Monte Carlo simulation, this virus 3.f for South Africa, but you can apply it. If you want, I can show it a little bit later how to do it, or tomorrow I can show the students how to do that. But basically, you have information on each lecture, with the YouTube videos. You can go here and watch the YouTube videos with each one is, introduction to epidemiological models, mathematical modeling of COVID-19, C++, Python applications. And the last one was about the Planck Monte Carlo simulations. And also, very interesting, the Android application coming from that Monte Carlo simulation, where we did some Java. Actually, Amaro did some Java, and the paper and his code, his Java application is here for the Android. You can get it there, and you can download it, right? But I will show a little bit of how it works later. Basically, this one. That's it. All right, so we continue, and here we have also lots of videos on my YouTube channel, which actually we open to keep motivating the students. I opened this just before, or just while we have COVID-19, to get the students excited about going to the different conferences, talks by different speakers at the Taste of Nuclear Physics. Again, I can show you a little bit here. This is the web page, and you have online pracs that we are running right now for students. But you have the new frame, the Gamka, the Lion here, and different playlists And here we have in COVID-19, we have a bunch of playlists here, but you can see lots of interesting stuff that we posted to keep the excitement going, right? And also, I was hoping actually that eventually we'll reach 1,000 subscribers. We have 390, so we could collect some funds, to support our students as well, because many of them, they come from poor areas, and it was I thought that we needed to find any means to support the students. If one day we reach 1,000, so we can start collecting some money to support our students. So I will encourage you to subscribe and watch some of the beautiful videos, which are mostly for nuclear physics, but not only, also for physics 111, for teaching purposes. All right, so now we keep going down. I will introduce a little bit of on the SIR model. So, which is a good approximation for the spread of viral diseases, because you always go in one direction, not like with bacterial infection, which you can go back and get infected again. So we have a population of susceptible, which, as I said at the beginning, this N is the total population of susceptible plus infected plus recover. And this is one of the conditions of the system for a fixed population N. Any changes due to spatial migration, lifting of lockdown restrictions, etc., are not considered in the model. And this must be clear, because if something happens, the model will fail automatically, after a few days, because remember, we are dealing with death. So there's a time of about 20 days for people to die once they get infected, 20 plus minus 5 or so. So as soon as there's a change, we'll learn later on, about 20 days later, there will be an effect in the trend.
One question, old paper. Yeah. This paper, it's very old here, long time here. It's examples here, 1927, right? It's old.
Oh, this paper here.
Right.
Yeah, this is a proceeding of the Royal Society. That's 1927.
Okay.
1927. It was actually the first time that the SIR model was introduced, almost 100 years ago, right? This is proceedings is freely available to everyone. This is the Kermack-McKendrick paper, very famous in epidemiology. So, is that okay, Grant? I don't know who asked the question. Okay, we continue, and as I say, there's no way back. It always goes. We have a transmission rate, we have a recovery rate, or a removal rate. Either you recover, means that you recover, or you die. So there are the two possibilities. But again, as for the cow disease that we have in 1918, to keep the population fixed is very important if one has to assume that there may be a possibility for herd immunity. So if you suddenly open the system, obviously there will be more people, more infected cases coming in, and the situation will change. Also, the situation may change if you have a new variant, as we discussed at the beginning of the seminar. So, and this is the only way to have herd immunity in a realistic way, is by vaccinating the population. And this is a nice what is that? There is a nice web page. Let me start closing this one so I know. Here we go. So here you have the population in the US. Like 36.6% of the population has been vaccinated as of April 13. At least one dose. In the UK is 47. So you have, as you can see, Africa is at a different level. And I know that at Notre Dame, during the fall, most of the students must be, not this one, but I read in the news here that Notre Dame is requiring students to be vaccinated for the fall. I hope we were in a similar situation. But as you can see, it will take a little while for us to reach that that point. At this stage in South Africa, it's not even 1% of the population which has a vaccine, a one shot. So in the rest of Africa, as you can see, it's even worse. There's no data. So this is the case, and this is why I will invest more time in my predictions about South Africa later on. But everything can be extrapolated to the US, and we can also look at some of the US predictions. So okay. So all right. So we go down, and then here we can assume for the death model that there's no recovery. What does imply? Basically, it's a big assumption, right? So basically, this happens during the time of the pandemic, that the spreading rate is much larger than the removal rate. So, and then by assuming this is the infected cases, which we can reach easily, we can solve this problem. It's a very simple differential equation problem, which I have written here, and it's in one of the videos I explained in lecture 1. In the YouTube videos, you can everything is explained very nicely to students. But basically, if you assume that lambda is much greater than beta and r is equal to 0, you can simplify the four equations, the dynamic equations for the viral spread, right? RT is equal to 0. So basically, you have that di dt, you get reach this differential equation, and you can solve that differential equation easily. This is just a little math problem, and you reach these infected cases, and you parameterize, you remove all these constant, you parameterize the constant, this spreading rate, the total population. This is a big coefficient or B parameter, and eventually you have this function, which has an exponential in the numerator, exponential in the denominator. And as I say, these are very sensitive to the different phases of the pandemic. So basically here we make the death function as a function of the death rate times the infected rate, the time minus the death time. This is the death time, which I said before is about 20 days plus minus 5 or so. So we reach a function, which is the death function. And these parameters are also important, A, B, and C, and they all have a meaning. You know, the parameter A is the theoretical number at time equals 0. How many deaths you have at time equals 0, right? And generally, when you are doing the feed into the data, we solve analytically the system of 4 equations into this simple equation here, assuming, and again, I say, assuming no recovery. But all these parameters have a meaning. The parameter B at the exponential phase it tells us how long it will take for the death to double, the death numbers to double, and also it is just related to the full width of the distribution, as the full width half maximum is 3.5 times B. So again, everything is statistics, everything is mathematical methods, and very important, which I will mention later, are the time dependence of these parameters. You can see they change with days, and we assume here in this equation, which they are constant, but truly they depend, and every time you change a lockdown effect from 5 to 4, from 3 to 1, things may change. So again, these models work under similar conditions, right? If you change the conditions, you can do the derivative, you can play apply L'Hopital, and if you apply L'Hopital, you see that the limit to infinity on the time will be, you have as time goes to infinity, the total number of deaths will be A over C, right? And basically you just apply mathematics and you get lots of information. You get the inflection point also by doing the second derivative equal to 0. So the inflection point is B natural log of C. But let's go to the presentation. There are a lot of information which I don't want to overwhelm you with. So basically, this is the point. No recovery, assumption of no recovery, and let's see whether this makes sense or not later on. As I was just saying, these are the different parameters, depends on the death time, on the B here. The B is the characteristic evolution of the initial exponential increase of the pandemic. As I say, B tells you in how many days the exponential will double the number of death cases. Or parameters, they represent, this is very important, space-time averages, right? So this is very important to say, because at the end, this is something that needs to be investigated. If we can deduce what is the time dependence of these A, B, C parameters, we may have a chance to understand or to predict the pandemic evolution more precisely. And this is something that we need to investigate. So, okay. So all this, keep in mind what Freeman Dyson came to Enrico Fermi. Freeman Dyson was a nuclear physicist at that time. He discussed his model with Enrico Fermi. This is published in Nature. How many arbitrary parameters do you use for your calculations? Enrico Fermi asked Freeman Dyson. I thought for a moment about our cutoff procedures. Freeman said 4. But he said, I remember my friend Johnny von Neumann, who, as you know, invented the computer, used to say, with 4 parameters, I can fit an elephant. With 5, I can make him wiggle his trunk. With that, the conversation was over. Freeman Dyson escaped to Berkeley to start a new career in condensed matter physics. So as you can see, nuclear physics has never been easy. Freeman Dyson learned it the hard way. Obviously, we need more Enrico Fermis to tell us sometimes where we are wrong. So, but we try always to reduce this number of parameters, and we have the reduced D2 or reduced models where they are also explained in the paper. So now everything started here with Wuhan in China, and let's see how this model really applies. So we explore the situation in China. Obviously, everything fit very nicely with the data. Also for the deaths per day, these are cumulative deaths in China, which I always found very surprising that you only reached 3,500 here, and that was it. And deaths per day, also they agree with the data. So basically, our analytical solution seems to work. Allows the D model fit to data and explore pandemic evolution as new data coming. Obviously, the more data you have, the better. The more statistics, which is not good for the country, and the more data you have, the better. And as time comes, the more data you get. So as I mentioned before, the D model predicts the end of the exponential phase, right? Much earlier than, whenever you see this difference, obviously you are out of the exponential phase, but much earlier. Like this was like in May 29, we didn't know, we were not very sure about where we were in this scary exponential phase where everyone is going to die, or we're going to flatten the curve soon enough, right? So this was a way, because we have this exponential in the numerator and this exponential in the denominator, and these parameters, they actually predict very nicely the exit from this exponential phase, going down to this slow down phase where you flatten the curve. So also the D prime, the first derivative, worked very nice. This was for South Africa, and again, this was quite successful. Also, for the pandemic peak, as I say, we can predict it with the deaths per day, but it's more relevant to do it with when you have more statistics, as I say. So deaths per day, you can have like 200, you have lots of fluctuations. So it's always better to go to the cumulative deaths, right? Because here is the inflection point what really matters. This, as I say, minus B natural log of C. I think I will show it later. Oops, I think I went too far. I press the wrong thing. I think I better speed up, otherwise we're going to be here until here we go. Right. So okay, where is the pandemic peak? As I mentioned before, predictions improve with more time and data. As you can see here in the United Kingdom, 29th of March, 17th of April, 17th of May, and you know how the bands, the error propagation change from curve to curve as time goes on. Oh, again, I go to the end. What's happened now? Okay, here we go. All right, and this is a very important part of the predictions. So we have, for the case of Spain, let's say a population of 1 million. We calculated the infected for different death times of 15 days or 20 days. They are very similar, and they reach a plateau about 1 million here. So basically, the whole population get infected because there's no recovery, and there's a small population which die, and the small population is represented here about 1.5% or 1.6%. This is the death function over the infected function. And but very important to understand that most of the population get infected. So the COVID-19 virus is extremely contagious, but as we shall see, most of the people become asymptomatic because this model doesn't assume recovery, right? So there must be something, and we shall see later how, when we assume recovery, things match with each other. So basically, this approximation of people becoming asymptomatic from the death model, it seems to be a good one. And here it came also in many of the news that the models predict most of the susceptible population get infected and asymptomatic, and 86% of the UK's COVID-19 patients have no symptoms. So many people got the COVID-19, but they didn't show any symptoms, not only in London, but also in South Africa. So there was lots of news happening that you know, COVID-19 is very, very contagious, but you know, the numbers of death, the ratio to death to infected was like, as you know, 1.5, or you know, some places was 2%, depending on the situation. So then we try to apply our thinking to the extended SIR model, including recovery. At that time, we needed a boundary condition to solve the equations. But basically, as you can see here, actually, let's go to these are some formalism that we use to deduce the extended SIR equations. But as I say, you need some boundary condition to solve the problem. Otherwise, this always goes to the as a plateau. Never comes to zero, the deaths per day. So as soon as you included that the first derivative of a number, 100 days, is equal to 10, you give a value, then obviously the curve comes down, but doesn't matter, you can give 5 and the same number comes down. So, but the important fact here was that A over C, which I mentioned here before, A over C, as time goes to infinity, the recovery goes to A over C. Again, I pressed the wrong button here. Let me see here. Let me see. Here we go. Okay, here we are. So basically, most people recover as R tends to 1, right, for large T. So basically, again, the extended SIR with including recovery predicted that most people recover as we go as time goes to infinity, right? So this is the case, as I mentioned before, if the situation is ideal, right? There's no opening, we keep the population constant. So in such a situation, it seems that herd immunity applies, but obviously we are not considering the reality of life, which is the virus may mutate. There are openings, people move from here to there, they move to the towns. The situation is much more complicated than what the model predict with the conditions of the SIR equations, right? So here is the conclusion. The two models, when we combine the recovery and no recovery, they predict that most population recovers at the end, so reaching some kind of herd immunity. But as I say, this depends on the validity of the initial conditions. Again, we can apply the extended SIR model like we did for the death model. We can have two of those equations. The same thing, we can have two death functions to represent two different waves, for instance. And here we have the situation, how the death model and the extended SIR, they come to a very similar conclusions here. This was in the US in June, 19th of June. So you can see here that the extended SIR model predicted very nicely. I don't know if we can zoom in this a little bit. Predicted much nicer. The chi-square per degree of freedom was better here. And similarly in the United Kingdom, Spain, and other European countries where we studied the first wave at that time. So the extended SIR model normally gave a little bit better chi-squares rather than using two D functions. So and not only that, we got encouraged by seeing that the SIR2 model predicts overall trends. So we applied further, and we normalized the D function in a way by shifting the function by the inflection point, T max equal, as I mentioned before, minus B natural log of C, and dividing by the total number of deaths, right? So if you do that, as you can see, all the different countries come together in a kind of universal pattern for COVID-19 pandemic. For the evolution, you can see is a typical Wood-Saxon potential, right? And as you go for the deaths per day, the situation is not as clear because you don't have enough statistics probably, or because there's much more fluctuations in the deaths per day than in the cumulative deaths, right? So this was a very interesting point for us to understand, because it may imply that there's a way out. We may actually solve the SIR equations. As I don't have much time, 15 minutes or so. Today is the World Quantum Day, and again, lecture 4 in the GitHub is explaining the Monte Carlo Planck model very well. But basically, we are applying the distribution invented by Planck for the photons and for the black body radiation for our particular case, where in this case the temperature will be how many rounds to the perimeter, to the range you have done, all this. There will be a grid of, or a lattice of two-dimensional lattice with each point, where each point considers a susceptible, infected, recover, or dead. So we are going to be able to predict with time a function for the susceptible, infected, recover, and death, and the increments for each of those. So we repeat the calculation for each day, and this is actually I have the calculation here. This is the Fortran file, and you can quickly get the let me see, ls2, and you run your Fortran file, and you get all this. So basically, you play with the parameters, and you get this function here, which is this virus3, the one which I just ran. I just plotted it here, and these are the numbers of cumulative deaths for in South Africa for the second wave, which agrees quite well with the predictions. I mean, with the real data. So I could show you a little movie on how this works, because this actually, I think, let me see what it is. Find minus name MP4, and I can show a little bit of, let's see, South Africa. Let's see that one. What has the? Here we go. You see, so this is the application for your Android that you can get from Amaro's webpage, which is here. Let's see here. So let me move this guy. So basically, with Amaro webpage, I probably remove it now, but it's basically ugr.es/Amaro. And right there, you can see this coronavirus. And right here is the pandemic app for the Android. So each of you guys can download this, save it, run it in your cell phone, and basically you can run here the length, the range, the recovery time. You have different parameters, and basically it tells you on your Android if gives you a Monte Carlo simulation of the pandemic. This is not very exciting, but let me just show you actually a better video here. VLC South Africa edit. Here we go. It's more exciting. So as you can see here, you start with a susceptible, say 90,000 population, because the computer cannot take, or your cell phone cannot take more. So you keep running it, right? And you see how the susceptible population changes to infected, recover, and one death here. So let me see, I got it further. Let me see. Sorry, this Zoom. Anyway, you can run it yourself, and you will see very nicely how the pandemic spreads, and we use it for the kids, for the students, to understand how you can stop the pandemic by playing with the different parameters and by then running a Monte Carlo simulation, right? So that's also a very nice tool to have to create this pandemic awareness, right? So here we have the more explanations, the typical cross-section, the Planck distribution, where you assume the energy is quantized, and all these things. The temperature of the system, as I say, is how much you move. The more you move, the higher is the temperature. And as I mentioned also before, and you have these parameters in your Android application, you need to play with them. And normally what we use is the death model to get the parameters for our Monte Carlo simulation. So the death model is our first approximation. The parameters are related to these ones. And that is our first approach to deduce what is the Monte Carlo for the particular country, right? And this is what we did for Spain, for Sweden, for South Africa, for the first waves. Again, as I mentioned before, T determines the average energy of the individuals, which is related to the mobility within its range of interaction. And N is the energy of the individuals. So I mentioned this already, the web page, and these are some calculations that we did for the second wave in South Africa. As you can see, the second wave was much bigger. Our Monte Carlo simulation has the difference between the first wave and the second wave was that the pandemic actually for the second wave has a larger death rate than the first one. So that became more mortal in that sense, more deadly. So, and this is the typical snake situation when you have first wave and second wave. We never really flatten in the first wave. And here, hopefully we are flattening right now. But we predict a total deaths of in South Africa of 63,000. And this is very important also for you guys to know this death excess is not considered in the model. You know, we have 153,000, almost 154,000 excess deaths from 3rd of May to 10th of April 2021. But you know, this is an argument against all this COVID-19 modeling, because we never predict such a big number. The real number, obviously, we are getting the numbers from the hospitals, COVID-19 from worldometers, you know, these are official numbers, but the death excesses, you know, the excess death, sorry, they are much more, you know, 153 versus 63,000, right? So they are more than 2 times the death cases that we see from COVID-19. So one could argue whether this modeling is valid if we don't get the total number of deaths. Obviously, it's not written here, but all these death excesses, they seem to be related to COVID-19, or these fatalities. You have it here. This is the prediction for South Africa. And you see that the death excess, right, it follows a very similar pattern to the actual deaths from COVID-19. And you have here the comparison of the excess deaths versus the actual COVID-19 situation. These are deaths from hospitals and the different modeling that fits to the data. So as you can see, actually there's almost a 1-to-1 correspondence. The peaks are the same here and here. And this tells us that even when modeling cannot predict the total amount, the magnitude of the deaths, it can predict the trend and the evolution of the COVID-19 pandemic, and predict the peaks, the end of the exponential phase, or the end of the pandemic, right? So seems to be that we have enough representative data to play with the data and reach some conclusions which may be valid. So another thing is, how do we predict a third wave? So a third wave here, you know, this is for the Western Cape. The Western Cape also follows a similar pattern to the whole South Africa, but now we can go to different regions, let's say New York and California or whatever, right? So, but we see that, you know, there's a shift in between how the waves come. So this for the Western Cape comes first. You know, Western Cape is Cape Town. You know, it's the most beautiful city in the world. So everyone wants to come to Cape Town, right? So everyone is a source. Number N is never constant in Cape Town. Everyone wants to come here. So with the pandemic started here in the Cape Town area, and then it shifted to the rest of South Africa, right? So here is South Africa, this is Cape Town, and the same thing happened for the second wave. A little bit less difference because now the pandemic was more spread, but again, Cape Town or Western Cape starts before the rest of the country, right? Then the pandemic spread throughout the country. It's like going from the east coast to the west coast in the States. So this may be an indicator for a third wave, because if you look at the data, you know, other countries are more isolated, like South Korea, Uruguay, but you know, Cape Town has a large flux of tourists and population, and people want always to come here. And as I mentioned before, what is important is that both South Africa and Western Cape present a similar trend with a slight delay. And then we look at the death ratio of the Western Cape over South Africa, we'll see that, you know, it reached 80% death in the Western Cape, mostly in the Cape Town area, but not only. And then it comes down, spread throughout the country until you reach a minimum. So most deaths are not happening in the Western Cape. 21.2% of the deaths in South Africa here happens in the Western Cape. And then suddenly on the 27th of May, there's an increase again. And in this 27th of, November, there's again the indication of a second wave. Already before it hits on the maximum in January, we could predict with time that it would have been wise to have a lockdown during Christmas time, and maybe this second wave would have been so hurtful to the South African population. But these things are difficult to know a priori. These are things that we investigate as time goes on. And here is again assuming of the same thing, 27th of November, and this ratio corresponds to the actual death cases here that we see in the actual data, right? So it's very interesting to see this shift. In the US, the same situation, I would say, will happen maybe in New York. Everyone wants to go to New York, or maybe California, I don't know where will be the priority. But you can understand you just check the ratio of between what you think. I don't know, in the US, I would say New York and Chicago, say for instance, although the people in Chicago may not like what I'm saying right now. But if you check the ratio, New York versus Chicago, or the state in particular, Illinois versus New York, and you see that there's an increase in the sudden increase. Actually, no, they say New York with respect to the rest of the country. Sorry, New York with respect to the rest of the US. So if there's a change, and you pick up more in New York than in the rest of the country suddenly, then obviously this is an indication for a third wave. How this third wave happened? Mostly in the Western Cape in New York, for your particular case, it depends on the different situations, right? So in complete preventive measures, life conditions here in South Africa, for instance, in townships along the N2 highway, there's a lot of townships in Cape Town, unfortunately, and all these preventive measures are not always fulfilled. When you live in a shack, that's difficult to happen. So there's some social, economical situations there. As you can see here, most of deaths at the beginning, they happen in all these townships, Khayelitsha, Clifffontein, Tygerberg, all this area where townships happen. So this is a claim for everyone, that we need transformation. Otherwise, it's very difficult to control the spread of a pandemic. Also, why this may happen in the Western Cape before the rest of the country. Here we have these non-communicable diseases which happen in the richer areas, basically the diabetes, cancer, heart diseases, and this happen mostly in this area, in the Western Cape, also in the capital here in Gauteng, with respect to other countries. So as we know from the WHO, most people with high blood pressure, heart and lung problems, diabetes, obesity, or cancer are at higher risk of developing COVID-19 serious illness. And as I said at the beginning, this GREAM subject, we have been using it for a new platform for science outreach, teaching and learning. This is what we have learned also from our teaching and learning experience on how to use all these tools that everyone knows now. I haven't shown anything about that, but you can look at the videos, what we do during teaching and learning. As I say before, we have gone through different universities and explain high schools, universities. We're trying to spread this awareness and this STEM force for transformation, for science transformation everywhere. These are the University of Pretoria, student feedback on the model practicals. It was nice to hear from one of the authors of the topic. I made a little video for them. And all this is available if you go to the YouTube. Again, you can, everyone, this awareness campaign, try to stop the pandemic. And you learn how to use a Monte Carlo simulation at the same time. And which come back to the question. Let's go back to the original question. If I have a couple of minutes, Maxime. Just can the models predict herd immunity? So the answer is yes, but under stringent conditions, right? Like for the cattle, we need to avoid the introduction of foreign cattle basically there must be no mixing or not open system. Not only that, but also we need the virus not to change. If the virus changes and suddenly there's a different death rate, as we found from the first wave to the second wave, we know that the second wave was mainly a different variant from the first wave, right? Different virus, and this virus was double it had double the death rate, because we have doubled the number of deaths. Also that affects the original SIR equations, any models, that they are so naive and simplistic, but the situation is much more complicated than that, and some people try to accommodate that by having 35 parameters, like with realistic nucleon potentials. They go to 35 parameters, but they always keep in mind Enrico Fermi's approach. As I said before, yes, there is a herd immunity under those conditions, that nothing changes. There's no opening of the system. The system remains. But are they realistic conditions? Difficult to know nowadays, where transportation and moving from here to there things go very fast in these times of globalization, and also in these socio-economical situations where there's large differences between people, right? Between populations. You cannot afford to have a constrained COVID-19 in the townships of South Africa or in the poor areas all over the place, right? So very important to understand is how these parameters change with time, and let's see whether we can make something out of that. Just to keep investigating, maybe we can come with some smart ideas, like Isaac Newton came when he has his pandemic in 1665-66, where he discovered he wrote his famous philosophy of science, right? Where he discovered the gravitation theory, the light, the theory of light, the Principia, sorry. And as I wanted to outline, always transformation is priority. As Nelson Mandela used to say, education is the most powerful weapon which you can use to change the world. And I'm very glad to be with you today, and thank you very much for giving me this opportunity. Thanks. I'm going to stop sharing now, and then we can.
Okay, so thank you for your talk, Nico. So we'll take some questions.
Of course.
If you have any question, raise your hand electronically.
Okay. Sorry.
Or just start talking.
Okay. Talks about no beef from Brazil to, right? Can beef from Brazil? Yeah, it's dangerous.
Yeah, in Brazil, it's not very good right now.
Check, right?
Brazil. Okay, we can check in Brazil. If I can share the screen now, I can ask any questions. We can plot data as I say. We have automatized all this. So I'm going to close this. I'm going to close this. I'm going to close the Fortran. Let's see what happened in Brazil. So let's see. We have so I will tell you that this program, we have all the programs. So we have a script on the GitHub. It's called script.py, and we can compile it with we can run it with Python 3. We will collect right away all data from the worldometers, right? Automatically, the new data from worldometers, USA, Brazil, India, Russia, for as many countries as you have in the script. And this is, as I mentioned before, is all here. Here we go. UWC Nuclear. If you go to COVID-19 mini school, so you have all the programs here. I'm using this old code, but and you have the script.py, which works also very nicely. And this is the code, the C++ code that we're going to use now within root, right? So then we have collected the data. We have already collected the data for Brazil, and we can go to to South Africa and see whether they, it's very fast. Whether it's a third wave coming, we don't know. There's a little bit of a kink here, and this is a question mark. I leave it there because it's not clear yet. We close here. We can close. You see, we can go. We can integrate whatever we want there. South Africa. Let me see. Israel. I was looking at Israel. Norway. Different countries. Let's go to USA. This is the reduced model, which is crazy here. But if we go a little bit more into detail and have the non-reduced model, things become a little bit better. As you can see now, this is the D model, just one D function. If you have two D functions, I'm actually just fitting from here to here, and you can see that the D prime 2 and the extended SIR model, they fit the data quite nicely. We can go to Brazil, but Brazil, we may have to change the limits. Brazil, and let's see what happened in Brazil. So in Brazil, we may have to. It's going up, but let's see. Let's change here. Let's integrate. Let's fit from here. Say from 11th of November. So also this, most countries. 11th of November. Let's see what happened now. Still, this is going up, and this is going up. So we have two waves, and we don't know where we are going to stop here. Brazil has been always a difficult country to predict, because you have all these kinks and up and downs. It's a difficult country to predict, but the situation is not good at this stage. But we can improve things, but we have no time to improve things for Brazil right now. Unfortunately, the situation, as you say, doesn't look good. There's another wave coming, and we don't know when it will stop at this stage. We can actually have a look here. Maybe we can make a fit from the 20th of February for Brazil of 20th of Feb. Well, that didn't work out. It was the wrong country, probably. The wrong date. 20. Here we go. 21. Right, and this is a better fit of the situation. And you can see the error propagation is quite large. This one is nonsense because just one D function. You need two at least to predict these two kinks, these two situations, which may happen. I don't know about the lockdown conditions in Brazil, but you can see it seems to be reaching a maximum according to the D2 model, but the extended SIR model still is giving you a large error propagation. So I wouldn't be convinced, but there's a first indication that from this model that you may be reaching a peak sometime soon. What I will do is that I always expect these two to converge, and then you make a prediction in a much better way. So if you want, I can show you for any country you want to at this stage, but you can run it yourself. Basically, what you do is I'm going to quit. You just press root. Actually, let me see what is the latest root. ls2.c. So I'm going to take this root, which is in the GitHub. I can root -l, and then I can compile that root. And for any country, as I say, I can Brazil, USA, South Africa. I can integrate the D2 function and see how many deaf people are. I can run it for any country I want. From Turkey, whatever, you can run Turkey, and then Turkey again has another wave coming. So Yeah, so we are never safe, hopefully, until we have a herd immunity. And from a theoretical perspective, herd immunity happens under very stringent situations, but in reality, it's not the case. Any more questions?
Any more questions? In one of your model, on one of your slides, you put what was your model versus the data in May 15, 2020 or something like that?
Yeah.
Or
the exponential phase, or what
yeah,
was it?
for South Africa, yeah. And do you have then further data? I guess we know what happened since.
Yeah.
How does like your model fit? Like
Actually, it did
with
pretty
the
well
added
because
data afterwards.
it did pretty well because we predicted around 15,000, and this is what we got at the end. We got 18,000 during the first wave, so it wasn't too much off, right? From it was 16,000, and then the total number of deaths was around 18,000. So it did pretty well from that point, that prediction, where still it was climbing up, right? And we didn't know what will happen afterwards. I mean, again, this needs some kind of it's easier when you reach the peak. The parameters became much stable, very, very stable in the way down, because basically it's just coming down slowly if nothing else happens in between. But again, the situation may be suddenly we change the lockdown effects here and there, and then the situation changed completely, right? The model doesn't apply anymore.
So typically, is it the case that for most country, you need to have a minimal adjustment of your fit parameters, or how much do they vary? As you add more and more data and you fit over and over from one day to another, your fit parameter will change as you get more data.
But here you have we can go quickly. I will show you in the paper. We have in the paper actually not this one, but here we have a comparison of all the countries that we did at that time, and you can see that this is why we have this. And I don't know if you can see the figure. I'm trying to get the figure bigger. But you look the plots for Germany, Italy. Here we go. This is a nice feature. I didn't know. I just need to remove Umesh from here for the time being. So as you can see, the parameters, they change, but the overall shape, about 100 here is a little bit bigger. So here you have the two functions, right? We have the 2D functions, 1 and 2, two waves basically representing the going up and the coming down. So it's always the same situation. You go up very fast and you come down very slowly because the virus keeps spreading throughout, and you release the lockdown measures, right? So you have, but as I mentioned also in this paper here, if you, there are special cases like in the US where everything eventually became crazy here. But if you plot things and you make this normalization function, you can see that all the countries, they come together in this normalized function for the, in this plot, for instance, you have the USA, Spain, Italy, United Kingdom, France, Germany during the first wave, right? So there seems to be a kind of a universal pattern, but still this universal pattern needs to be discover, right? It's not hasn't been discovered so far in so many years, and it's a difficult task. It's not otherwise everyone will be knowing what will happen next, and it's a difficult thing because things change quite a lot. It's a very complicated system, and only probably using statistical methods, and we can maybe find a solution. We keep trying and see whether we can reach any conclusions.
Any other questions?
I had a simple question, if I may.
Yeah, go
Do the
ahead.
lockdowns actually work? Because Sweden, for example, avoided the lockdowns. Other countries put them in, but it looks like they're all following the same curve.
Right.
Does that show up in the
So-
parameters somehow?
But Sweden, they didn't have a lockdown, but they were not stupid. These people, they didn't go and they still kept social distancing. They did masks. I mean, the kids went to school, but they didn't have a lockdown. But at the same time, they kept the safety measures, so which helped the situation. It wasn't the same as Norway, Finland, Denmark. They have much less deaths, casualties, or fatalities than Sweden. So at the end of the day, it wasn't a good idea not to have a full lockdown. But it's not like they didn't have a full lockdown like other countries, but still they have preventive measures all over the place. So I don't know. It didn't work out as bad as the media mentioned. There are many other countries where the situation was much worse, but maybe that's because of the medical system in Sweden is also much better than in many countries. The social welfare, the medical aid, everything is very good in Sweden and in the Nordic countries. So when you compare with Finland, with Norway, yeah, you lose. But when you compare with the rest, you win. So it depends what you compare with. If you compare with the US, Sweden won big time, So I don't know.
Okay.
Okay,
so we don't know if lockdowns worked or not.
Well, they work,
As
but
long as you social
work.
distance, if people volunteer to social distance, that's enough.
Right. I think. Well, you get a little bit worse situation. I mean, I think if you go back in time and the Swedish government will say, let's have a lockdown now because we cannot afford to have as many deaths as we had.
Okay.
So they were hoping to have probably more herd immunity. And there was this approach, but I don't think it worked 100% as they wanted. So I think as for the cows in 1918, it's better not to mix too much and not to go to, not to have a wide range of population moving here and there if you don't have a vaccination. So the lockdown worked to flattening the curve much earlier. So otherwise you will have an exponential phase for a longer time, and this exponential phase will kill more people. So obviously the lockdown worked in that sense that you isolated the country, and the number of number n, the total number for the population kept constant as much as you can. This is the only thing you can do when you don't have a vaccine.
Okay, good.
No other question? All right. Oh, all right. I'll thank you, Nico, again.
Thank you so much for.
Do you realize, Maxime, we sent both the loudspeakers to South Africa?
They are both.
Smarajit and Nico,
Yeah, it's true.
so that